Alright, greetings everybody, and today we're back at it again with some more complex analysis, and today we're evaluating this improper integral from 0 to infinity of x to the k over x to the n plus 1. So just before we get started, we have this restriction on n and k where their difference needs to be greater than or equal to 2, and this is just so this integral here converges nicely. I also know of some cases where you could have that the difference could be strictly greater than 1, especially if n and k are fractional powers. But just to keep things simple and to avoid branch cuts and singularities at the origin and all that, we're just going to assume n and k are natural numbers, and if they are natural numbers, then you need this condition right here that their difference is greater than 2. So if n is equal to 4, for example, k can only be 1 or 2, it can't be 3. Alright, so let's just jump straight into the solution right here using complex analysis. So naturally we want to define for ourselves a new complex valued function, let's call it f of z, and we're just going to be letting it equal to this integrand right here, but we're just going to replace all the x's with a z, so switching from real valid inputs to complex valid inputs. So we have z to the n plus 1 on the denominator right here. And we want to integrate this function f of z around some kinds of contour. And before we do that, we want to figure out where the poles are. So the poles. Where exactly are the poles of this function? Well, if you look on the top, z to the k is pretty much entire everywhere on the complex plane because k is a natural number. And if you look on the denominator, we have z to the n plus 1. That's kind of some kinds of polynomial. So it's going to have some kind of complex poles because we can have zeros on the denominator. So in order to figure that out, we just need to solve for when z to the n plus 1 is equal to 0. And I've done a video on this where I go through the solution in more detail. You can check the link up here or in the description. But what you're going to get is that the poles of this function occur where z is equal to e to the I pi over n times some kind of odd number, so 2k plus 1, where k is just going to, that's an ugly bracket, where k is just going to go from 0, 1 to all the way up to n minus 1. And it only goes up to n minus 1 because we don't want to repeat the poles, because if k is equal to n, then we are repeating the first pole. Alright, so we know where our poles are, and now we just need to figure out what our contour is. And our contour, we're going to be using a little bit of a, I like to call it a pizza slice contour, because that's exactly what it looks like. It's a pizza slice. So we have two rays going out like this, and then we just have an arc going down like so that makes some kind of a contour. And we're going to be traversing this contour in the positive direction. And why did we choose this contour? Well, notice our interval of integration is from 0 to infinity. So this is the point 0, and on this contour we're just going up to some point r, where I will be a very big number. So later we're going to be taking right here the limit as r approaches infinity. So when we integrate on this interval, in the limit it's going to match up with what we have right here. And of course we figured out the poles because one of the poles is actually going to lie inside of this contour, and that's the very first pole. So if you let k be equal to 0, then you're going to have e to the I pi over n. So this pole right here, I'll mark it in red. This pole, this is exactly e to the I pi over n. And how about our second pole? I'll just put that in just as a reference. Our second pole is going to be somewhere over here. So e to the I 3 pi over n. So we have 1 pi over n and 3 pi over n. Then the next pole will probably be over here somewhere. So e to the I 5 pi over n, if you can even see that. Yes, you can. So our third pole is going to be over there, and it's going to keep going around the circle. Of course, the shape of this contour and its dimensions and everything will be highly dependent on whatever n value we choose, but just in general, it's going to look something like this. This is the setup we have. So if our contour encloses one of these poles right here, we can actually figure out the value of this contour, we'll call C, using the residue theorem. And while I'm at it right here, I might as well name each of the following paths. So this path I'm going to call gamma, and the path going down I'm going to call psi, like so. Okay, and we kind of have an idea of what this path gamma is. It's just going to be part of a circle with a radius r. But how about this path of psi right here? Well, just to make this path more clear, how we define it, what we want it to do is we want it to pass directly in between these two poles right here. So notice we have an angle of pi over n, so going up over here, this is an angle of pi over n, and if we look at this next pole right here, we have an angle of 3 pi over n, so this whole angle is 3 pi over n. We want this psi path right here to have an angle of 2 pi over n, so the part of a ray which passes through both of these poles right here. So you can kind of think about this path right here as being part of the set arg z is equal to 2 pi over n, like so. And the reason why we choose this particular definition right here, it just makes the calculations in our integrals work out a little bit nicer. So with that out of the way, let's write down a couple of integrals. So first of all, we have the contour integral over c of f of z dz, and we can easily figure that out by using Cauchy's residue theorem. So we're just going to take the residue at this pole, multiply by 2 pi I, but notice that this path c can be decomposed into the path, well, first of all, we're going from 0 to r, so we have the integral from 0 to r, and notice that it's on the real axis, so instead of f of z, we can just put f of x dx, and then we're going to add the integral over gamma. So we're going to have the integral over gamma of f of z dz. And in fact, this integral, when you take the limit as r approaches infinity, it's going to vanish up to 0. I'm not going to prove that in this video, but it's something that's not too hard to do, especially if you've watched my other complex analysis videos. And finally, we have the integral over psi, that's a beautiful psi, of f of z dz. Alright, so we have all our integrals written out right here. So we have 4 integrals to evaluate, and now it's just a matter of evaluating each of these integrals, as well as taking the limit as our r approaches infinity, because this is what we want in the very end. So I guess underneath this row right here, I'm going to write out the result for each of these integrals in the limit as our r approaches infinity. And let's just start off by evaluating the contour integral over c. This isn't too bad to do. So contour integral over c of f of z dz. We can use Cauchy's residue theorem, which says that it's 2 pi I times the sum of all the residues that's enclosed in the contour. But notice there's only one pole in the contour, which means we only need to calculate the residue at z is equal to this pole right here, so e to the I pi over n of our function f of z. And what exactly is the residue of this thing? Well, notice this is a first order pole, so we can just use the definition of the residue. So we still have our 2 pi I, and then the definition in terms of the limit, we can write it as the limit as z approaches this pole. So we have e to the I pi over n, and then we have z minus the pole, so z minus e to the I pi over n, times our function f of z. But our f of z is z to the k over z to the n+1, and if we multiply that in, I'm just going to write it like this, so kind of combining everything together, we're going to get a limit that looks something like this. This looks a little bit nasty to evaluate, but it's actually not too bad to do, because in fact if you look on the numerator right here, as z approaches e to the I pi over n, this part, that's going to kind of go to 0. And notice e to the I pi over n, we said that was a pole of this thing, and also a solution to this polynomial right here. So if this pole is a solution to this z to the n+1, which is exactly what we have over here, we're also going to get a 0 on the denominator, and that just means we have to use L'Hopital's rule, because we have 0 over 0. So continue on down here, we have 2 pi I. Let's actually split the limit up a little bit. I'm going to take a look at the limit of this thing first, because that's not going to go to 0. So let's just split up the limit. So we have the limit as z approaches e to the I pi over n. So I'll just put brackets right here just to be clear. We have our z to the k. So that's our first part of the limit. And we also have the second limit. So the limit as z approaches e to the I pi over n of whatever's remaining right here, which is just this part, so excluding that z to the k. And we know we have to use L'Hopital's rule on that because we have 0 divided by 0 if we plug e to the I pi over n in. So differentiating the top, that's pretty easy to do. That's just 1 because that's just some linear function in z with a leading coefficient of 1. And derivative of the bottom is n times z to the n minus 1. Just some basic power rule right there. Alright, and where can we go from here? Well, this limit's pretty easy to evaluate. This is just 2 pi I times, we can just plug this e to the I pi over n into this z, and we obtain e to the I. We can distribute this power inside of here, just multiplying those two powers together, so we'll get e to the I k times pi over n. And for this part right here, let's bring up this 1 over n to the front. It's just a constant in terms of z, so we have 2 pi I divided through by n. And then we have z to the n minus 1 remaining, but I'm going to flip this up to the numerator by multiplying a negative inside of here. And if we multiply the negative inside of the exponent, and we have a negative right here, we can just switch those two terms around. So we have z to the 1 minus n. Also, I forgot the limit, so we should have the limit first. So we still have the limit that's still there. So limit as z approaches e to the I pi over n of z to the 1 minus n. Okay, so we have that now, and where can we go from here? Let's get rid of the 0, it's kind of in the way. Notice we can split this up a little bit, so this is z times z to the minus n. So let's just do that replacement, z times z to the minus n. And notice if we plug e to the I pi over n into this first z, well, that's all good because it's not going to blow up or anything. Same deal over here with the z to the minus n, but the nice thing is when we plug this pole into z to the minus n, we have this n and this 1 over n in the exponent that are going to cancel each other out, leaving us with just e to the minus I times pi, and that's exactly negative 1. So in fact, if we plug e to the I pi over n into this second factor right here, we get a negative 1. And if we plug z equals e to the I pi over n into this first z right here, well, that's just this pole. So overall, what did we find? So let's rub out all of this stuff right here. We don't need it anymore. So overall, we still have this 2 pi I over n, but we're going to introduce a negative. So negative 2 pi I over n, and then we have e to the I k times pi over n. And then in the limit, well, we dealt with that negative 1 that we got before, and we just have e to the I pi over n remaining. So that's pretty much our residue, and I guess we can just clean things up a little bit more right here, combine these two exponential terms. So this is minus 2 pi I over n times e to the I. We can factor out that I as well as a pi over n, so e to the I pi over n. And then we have a k of those and 1 of those. So factoring that out, we get k plus 1 like so. And this is exactly the value of the contour integral over c of our function. So in the limit right here, as r approaches infinity, this contour will still enclose this pole. So the value of the contour doesn't change. So in the limit as our r approaches infinity, this integral becomes exactly this value right here. So minus 2 pi I over n times e to the I pi over n times k plus 1, like so. Alright, very nice. So that's our first integral evaluated. And let's move on to the second integral. So the second integral is this integral from 0 to r of f of x dx. That's extremely easy to find the value of because in the limit as our r approaches infinity, integral from 0 to r of f of x dx. Well, we can first of all take the limit as our r approaches infinity, so that's the integral from 0 to infinity. F of x, that's exactly f of z, but with the z's replaced with x, so we have x to the k over x to the n plus 1 dx. And notice that's exactly the integral we started off with. And this integral, I forgot to do it at the very start, but we're going to call that integral I, just so we know what we're solving later on. So this is exactly our I right here. So in the limit as our R approaches infinity, this integral turns back into I, which is basically what we had at the very beginning. Alright, so that was quite easy to do, and we're going to move on to this integral right here. This integral, I'm not going to go through it in this video because it's just going to be a waste of time, and I've done plenty of videos where I go through examples of calculating the integral over this big arc right here. The process is quite similar every single time, so you can just watch my other videos, get a sense of how to evaluate integrals over this type of path, and then just apply it to this integral. I'll leave that as homework. It's really not too difficult to do, and it's also a case of Jordan's lemma, because Jordan's lemma says that if you have the integral over some arc gamma and you have the limit as our R approaches infinity, so I'll call this gamma R, I guess, and if you have some rational function R times some kinds of exponential function, so something like e to the I a z dz. So if R is a function of the form P over Q, where the degree of P minus the, actually it's the degree of Q minus the degree of P, so degree of Q minus the degree of P is greater than 2. So if this thing's a rational function, and if you have P that's a polynomial and a Q that's a polynomial, and the degrees differ by more than 2, then this integral goes to 0. So I'll also link Jordan's lemma video up here or in the description. This is exactly in this form because we have polynomial over polynomial, and we have this condition here as well. So this integral over gamma goes to 0, so it's going to add absolutely nothing to our contour. And finally we have the integral over psi of f of z dz. So integral over psi of f of z dz. This one we need to parameterize it a little bit because it's a bit of an odd path that's going down in the complex plane. So how do we parameterize this thing right here? Well, notice that on our psi right here, every single z can be expressed as some kind of multiple of the complex number e to the I 2 pi over n, because notice we have an angle of 2 pi over n right here, which is exactly what we want, and e to the I 2 pi over n is just going to be some complex number that's a distance of 1 away from the origin, and if you kind of scale that by some parameter t, then you can actually obtain all the points on this gamma right here. And right here, t is going to go from R and it's going to go to 0, so from R to 0. And that's going to ensure that we start all the way up here. So we're going to start at R times e to the I 2 pi over n, and then we go all the way to 0. Right, and then we also need to figure out the differential of this thing. So dz is just equal to, well, in terms of t, this thing's just a constant, so we're just going to be left with e to the I 2 pi over n dt. Alright, so now we can plug everything back into this integral right here. We have now the integral from R to 0. F of z, well, f of z was this thing right here, but z is exactly t times e to the I 2 pi over n, so we'll just plug whatever this is into here. So first of all, we have t times e to the I 2 pi over n, but this thing raised to the kth power. Then on the denominator we have t times the e to the I 2 pi over n. This is to the nth power plus 1, and then our dz becomes e to the I 2 pi over n dt, like so. Alright, so let's continue on with evaluating this integral. Notice that on the denominator right here we have an n, a power of n, which will cancel out up here. And that's going to just leave us with a t to the n, because e to the I times 2 pi is just 1. So we have the integral of, let's figure out what the top is as well. We have the t to the k times e to the I 2 pi k over n. So just combining those two powers right there, distributing and everything. On the bottom we have a t to the n plus 1, like I said before. And let's bring this constant out to the front as well. Or we can actually combine it with this exponential over here, because both have a common factor of I times 2 pi over n. So if we factor that out, we just have k plus 1 in the exponent like so. You can confirm that for yourself. If you have I times 2 pi over n times k, that's what we had over here. And plus 1, well, that's just e to the I 2 pi over n, which is what we have right here. So in fact, you can factor it like that. And we have a dt. And let's switch the orientation of this integral. So now we're going from 0 to r, and we have to introduce negative as well. Alright, so this is the integral we're dealing with, and notice that this looks very similar to what we have going on at the very start. I'm just going to do a little bit more work, and maybe you'll see it. This is now negative. Let's bring this constant out to the front right here. So e to the I 2 pi over n times k plus 1. Now we have the integral from 0 to r of t, and notice t is just a dummy variable. Let's replace it with x, for example. So x to the k over x to the n plus 1. So we just made a variable replacement right there. And notice, this is basically what we have at the very start, but we just have this r. But remember, we want to take the limit as our r approaches infinity anyways on this integral. So if we do that, in fact, in the limit as our r approaches infinity, where should I put this? I'll put it back over here. Let's get rid of this. In the limit as our r approaches infinity, this thing becomes minus e to the I 2 pi over n times k plus 1. And then if this r turns into infinity, then we just have our I. So this is just some kind of complex number times our integral. So this integral contributes a negative e to the I 2 pi over n times k plus 1 to our contour, and times I as well. Alright, that's quite nice. We've done quite a bit of work, and now it's time to put everything together because we've evaluated all of our integrals. And remember, I is the thing we want to find at the very end, and we have some kind of algebraic expression right here in terms of I. So let's just solve for I and see what we get. So first of all, what can we do? Let's get rid of the 0. It's doing absolutely nothing. We just have a negative right here. And first of all, let's factor out an I. So because we have an I as a common factor, we can factor that out. So we have 1 minus this exponential term, like so. And let's get rid of this exponential on the left hand side. We just want all our exponentials on one side. So now we have 2 pi I over n. And what I'm going to do is I'm going to multiply by, I'm going to use a different color just to make it a little bit more clearer. I'm going to multiply it by e to the minus I pi over n plus 1. And do the same thing on this side as well. So this is multiplied by e to the minus I pi over n times k plus 1, as well as on this term. So multiply that by e to the minus I pi over n k plus 1. And what are we going to get if we do that? Notice that when you multiply these two together, we have the same base, and the exponentials differ by this factor of a negative right here, which means when you multiply them, the exponentials cancel out to 0, leaving us with e to the 0, which is exactly 1, which means on the left hand side we're just left with the minus 2 pi I over n, and on the right hand side we get our I that's still hanging around over here. And if we multiply this factor into this one, well, we'll just get that factor, so e to the minus I pi over n times k plus 1. And how about on this term right here? Well, this is exactly, notice this is 2 pi over n, and this is minus pi over n, and 2 minus 1 is 1, so in fact on this term right here we get e to the I pi over n times k plus 1, like so. Alright, that's quite nice. And now let's bring this negative and distribute it into this factor. So now we have 2 pi I over n, that's exactly I, times, now if we multiply negative into this difference right here, we're just going to flip it around. So we have now e to the I pi over n times k plus 1. And then we also have minus e to the minus I pi over n times k plus 1. So we're just switching these two around. And notice, if you take a very close look at this, we have e to the I times something. And over here we have minus e to the minus I times something. And that's very close to the definition of the complex sine function, except we're just missing a 2i on the denominator. Fortunately enough, we have a 2i waiting for us on the left hand side right here. So we just need to divide both sides by 2i, like so. And this 2 and this I will cancel each other out. And right here, that's our sine. So overall, we have now pi over n is equal to I times this thing right here, that becomes the sine of this argument right here. So pi over n times k plus 1. So pi over n times k plus 1. And that's basically this right hand side done. And now it's just a matter of isolating our I, because that's what we want to solve for. So I is now equal to pi over n over the sine of pi over n times k plus 1. And that is the final result for today's integral. So this integral right here is equal to this result. And you can have whatever values of n, k you want, and then you can just use this formula to figure out the value. So this generalization is quite nice. You can generalize it to many integrals of this form. You could also generalize it to if you have, for example, some constant alpha right here. If you do that, you can just do some algebraic manipulation and integral substitutions to get it back down to x to the n plus 1, and then you also have some kinds of random constant on the outside. But yeah, that's pretty much all for this video. I hope you guys enjoyed it, and until next time, have yourselves a wonderful day, and I'll see everyone later. Bye bye.